Well, hello to everyone who's joining us. I can't actually see any names or numbers, but whatever names and numbers you have, welcome. All right, going remote. Let me just get into full screen. Right. So I hope it's not a disappointment that I'm not going to be talking about high efficiencies in this talk. You'll have to tune into the presentations and forthcoming papers of my colleagues for that. So a bit of a different topic today, as Vincent was saying, a little bit about stability. So it's mostly going to be a technical talk, and I'll get into the meat of things rather quickly. But I thought it'd be nice to dwell a little bit on the high-level motivation for this. So I'm going to do that for a couple of minutes, if I may. So to put it bluntly, stability is the problem at the moment, as I see it in perovskite research. And I think that's a fairly uncontroversial statement, whether you're involved in this research or not. This is kind of the one sort of existential threat that hangs over us as a field looking forward sort of 5 or 10 years into the future. This is the one thing that really sort of threatens our livelihood, you could say. Another way to put that is that we've seen now big devices, we've seen efficient devices, but we haven't seen a lot of stable devices. And so, yeah, I mean, this has kind of been the case, you could say, from the birth of perovskites. The stability has always been with us as a major issue, but we've made major progress, I would say, on these other two fronts now, such that stability is kind of really the one thing that's holding us back in a big way. And so, I mean, I could also review now the progress that has been made, and there's been some very nice progress, especially relative to where we were when I entered this field a couple of years ago, quite a few years ago now. There's been very nice progress in stability, but I think it's perhaps more constructive for us to dwell on what's holding us back at this point. So I'm going to offer a little perspective on why that is, and I can see immediately that my slides have a problem here. I'm not sure why that is. My animation has come out of order here. So if you could ignore the text at the bottom, I'd like to describe to you what I see as the kind of status quo of stability research at the moment. And I was going to do that by presenting this little extract from a paper, which I've anonymized because the point is precisely that this is kind of the typical situation at the moment, and I have no reason to call out these authors in particular. But sort of the status quo at the moment in stability research is such that the typical paper is basically presenting one or another strategy for improving the stability of perovskite devices, and this can be maybe with addition of a certain chemical with some modification to the perovskite composition, or maybe it's a different annealing strategy, something like this. And the paper will typically proceed by showing, first of all, of course, essentially that this strategy works and improves the stability in some important respect. And then by telling basically a story, often coming after the fact to justify why that is. So this is okay as an approach, and it's got us this far. But I think, you know, given the sort of existential nature of this threat of the stability problem, I think we can afford to potentially do a bit better as a community. So I see two problems with this current situation, the status quo of stability research. And one problem you could say is that we don't do enough to characterize what's wrong with our baseline devices before we go ahead and modify them in some way. So I've drawn a little cartoon to illustrate the problem here. The issue is that we all have very different baselines, so we all have very different starting points, and our processes of fabrication can differ in you know, tens, hundreds of little details. So we all have different starting points, and given that fact, is, you know, the way I've illustrated this is the guy saying, you know, up is north, but that's not a very useful statement to the guy on the other side of the hill, right? So we have to know where we are to know in which direction to move to improve things. And of course, I mean, we're not dealing with a one-dimensional optimization problem here. We have many dimensions to think of and take care of. So the issue is quite severe. So that's one issue, that we don't thoroughly understand what's wrong with our devices in the first place before we try to improve them. And then the second issue is that we don't check what's still wrong with our improved devices once we've made the following measurement. So at the end, we've still got this delta in efficiency. It's not zero. And so clearly that can't be the end. I mean, this is not a stable device, although it's a fantastic improvement. We don't end up with a stable device here. So what's wrong with it? And how do we move on from there? So I think because we're not analyzing our degraded devices enough, progress is not really kind of cumulative in the way that it could be. And that applies both within and between groups. Yeah, so I mean, obviously, it would be nice to do better in these respects. And the thing that's kind of holding us back, I mean, the reason that people aren't doing this is not because they don't want to, but because we don't really understand enough about what causes perovskites to degrade. So more work is needed on the fundamental side, I think, to be able to differentiate different degradation modes and hopefully to establish clear and accessible ways of characterizing them. Because, you know, if you find a particular degradation mode that can only be characterized with the use of a synchrotron, then that's not going to be very useful to companies, for example, who are trying to figure out what's wrong with their product. You know, why are their devices not performing as they should? So it'd be very nice to differentiate different degradation modes of perovskite devices and have kind of clear ways of characterizing them, which, yeah. So I will return to this at the end. I have some propositions for what I think we could do to improve the sort of status quo of stability reporting here, and that includes doing some simple characterization, particularly in 2 dimensions, to see what's actually going on across our devices. So that's enough for the philosophy. I'm now going to move to the sort of technical part of the talk, and what I'm going to be doing essentially is describing one such degradation mode. So this work has revealed what appears to be an intrinsic perovskite mode of degradation, and it has to do with edges. So before I go any further, I'm going to define the terminology. So let me just be absolutely clear what I mean by edges here. So perhaps I can give myself a little pointer. That might be helpful. I don't know if you can see my mouse at the moment. Anyway, so what I've got on the left side is a schematic of the sort of device that we're typically working with in the lab. You could call this a laboratory prototype device. So every lab has their own specific geometry that they like best, but typically these devices are comprised of 2 partial area electrodes, and then you've got your active area, which sits in between them. Okay, so you've got some kind of substrate, usually it's glass in our case, and then your 2 electrodes will be typically a metal and a TCO if you're working with single junction devices. So we always have on these substrates regions of dead space, and then we have our active area. And sort of the key point that's emerged out of this investigation is that we have to be very careful what we mean by active area with these perovskites, because perovskites are not just semiconductors, and wonderful semiconductors they are, they're also mixed conductors, which means they have an ionic component to the conductivity. And we're not really thinking of that when we make this designation between active and inactive area. So although these electrode edges at the boundary of our active area produce a very sharp change in the electronic conductivity, they don't affect the ionic conductivity, so ion conduction happens, as far as we know, primarily through the perovskite layer. So wherever you've got perovskite, you have lateral ionic conductivity. And what that means is that your entire substrate is ionically active. This distinction of active and inactive areas simply doesn't apply when we're also thinking about ions. Okay, and a sort of corollary to that key point is that as you apply bias to the 2 different electrodes, you're affecting the entire substrate. The entire silver pad, for example, is affected by bias you put there, and the entire ITO pad is affected by bias that you put there. So naturally, we're going to drive ion migration into and out of these areas as we apply bias to our pads. And so we have to stop thinking that bias only affects the active area when ions are in the picture. So that's kind of high level overview of what I'll describe now in more detail in the following slides. But that comes very after the fact. So that might seem like a fairly simple insight. It's not the one that I started with by any means. And yeah, in fact, what happened, so the real course of events is that I started a project that was really on reverse bias stability. So our group at PB Lab has been working on trying to understand and improve reverse bias stability in perovskite cells for a couple of years now. And the fact is that I just kept running into these edge effects. I mean, I kind of tripped over them in quite a literal sense. I didn't come with this a priori understanding that lateral ion migration would be relevant, but rather it just kept occurring in my tests. So here I've got a series of examples where you've got basically an image of current flow in a little device showing strong localization of the current around the edge. In the middle, SEM showing a clear pattern of damage around the electrode edge. And then on the right, photoluminescence showing this clear pattern of darkening around the silver boundary. So I kept seeing these phenomena again and again, such that it became clear at some point that I could no longer ignore them. But a priori, there are many possibilities for explaining an edge effect. And ion conduction is certainly not the first one that came to my mind. And in fact, I considered a bunch of other possibilities first and had to work through them one by one before finally landing on this idea that actually it might be ions. So it's a little bit embarrassing for me to admit that. I mean, it took me more than a year of seeing these different examples of edge effects before I started thinking about laterally moving ions. And it's embarrassing because I spent a lot of my PhD modeling ions. I mean, my entire PhD basically was, was kind of non-experimental. I mean, I spent all of my time running models and trying to understand hysteresis and related phenomena. So I thought I knew quite a lot about ions. Nonetheless, this idea of lateral migration didn't really occur to me as being a relevant one. But anyway, as soon as I had the idea, of course, was a natural first step to consult these models that I'd developed over the years and to simply extend them from the one dimension, which we'd usually been thinking about, to 2 dimensions and see. So what do these models predict, given that they've been quite successful already in explaining hysteresis and related phenomena? So what I'll describe now is a kind of a little case study in this type of modeling. The schematic is showing the type of device that we're typically working with when we make single junctions. It's a bit simplified, but this basically contains all the essential features. So we've got our 2 electrodes, the perovskite in between, and some contact layers. In this case, we're working with self-assembled monolayers for the HTL and C60-based ETL. And so this case study that I'm going to walk you through is basically just looking at what happens when you have a boundary. So what happens when you have a boundary of your device, in this case, a boundary of the silver electrode. So I made these 2-dimensional models with a number of assumptions that I can go into if anybody is particularly interested. Vincent told me to dwell on the details here, but I don't think the modeling details are really going to be of that much interest to anybody, but feel free to ask questions afterwards. We make a number of simplifying assumptions, and the idea is to simulate this situation where we have active area that's in contact with a region of dead space. So we put metallic boundary conditions wherever there's active area, and then an insulating boundary condition for the dead space. And notably, I'm just assuming that this region of dead space on the right is kind of a source for ions, potentially. So modeling the case where you kind of have, let's say, notionally an infinite amount of dead space to the right of this device. Okay, and then the question is, what happens? So at t equals 0, before you allow the ions to do anything, this is what the field looks like inside your device. So because we have 2 electrodes, our ITO and our silver have different work functions, there is a built-in field. Okay, this is familiar. So the built-in field means that we have a potential difference between the top and the bottom of the device within the active area. But okay, as soon as you take away the electrode, you don't have that built-in field anymore. So automatically this creates a lateral potential difference, which can potentially drive ion migration. So we're very familiar with the built-in field driving ion migration in the vertical direction, so the direction out of plane. And basically now we're just looking at what happens in the other dimension, migration across this boundary. So indeed, once you move forward from t equals 0 and you allow the ions to migrate, you find that depending on what sort of ions we're talking about, so whether it's a cation or an anion that's mobile, you can have migration into or out of the active area. And it's happening on time scales which are relevant here. So you can see that these time scales, so I've chosen a fast ion just for this demonstration. So that's a relatively high constant of diffusion for the ion. sort of within the range of reported values for halide defects in particular. And you can see that migration is happening over tens of microns here in the simulation already at a few minutes. And then over hours, you can have relatively large redistributions of ions from one side of the boundary to the other. So factors of 10 in ion density as a result of this lateral migration once the system comes to equilibrium. So that's, I think, a fairly good indication that this effect stands a chance of being relevant, especially, now that we're testing devices not over minutes and hours, but hundreds, thousands, if we're lucky, tens of thousands of hours. There's certainly a chance for this type of migration to be relevant. So if we were justified in the early days in ignoring these effects because we were only testing devices for a couple of minutes or an hour, that's not the case anymore now that we're running tests for longer periods of time. Okay, so that's the sort of theoretical introduction. That's sort of setting the scene with the help of drift diffusion models, and I'll return to models a little bit later. But now let's move to the experiments. Let's look at the evidence. Are these effects actually happening? So this is an example experiment. It's a particularly simple one, I think, in which I've just taken one of my single junction cells. So the layer stack is described at the top here. It's kind of a standard cell stack for us. Notably, I'll just point out that we have two ALD layers in this stack. So we've got a tin oxide layer and an aluminium oxide layer, which acts as encapsulation. So, I mean, one potential cause of edge effects you've always got to worry about, okay, does the loss of encapsulation at the edge of my boundary maybe allow things to escape or other things to come in? But we took quite strong precautions in this work to make sure that that's not what's going on. We also tested these cells in inert gas environments. So anyway, so this particular experiment, we take one of our standard cells and we subject it to reverse bias in intervals. Here I'm just doing intervals of 60 seconds at -2 volts. And then I'm looking at the device in photoluminescence. So these images are sections of photoluminescence images of the whole device. I'm just taking cropped sections here to call your attention to particular features. And yeah, so we take images at intervals between these periods of reverse bias. And so what you can see is that at each of these regions, there's stuff happening. And in particular, we have propagating fronts at each of the boundaries shown here. And we also have activity occurring in the dead space, which is especially interesting and surprising. So this region that I've colored in black is completely in the dead space. We're far away from the ITO electrode. We don't expect any charge injection of electrons and holes in this region of the device. And nonetheless, we see this activity occurring at the device boundaries. Okay, so both of these observations, fairly strong evidence that something involving ions might be going on. I mean, it's very hard to explain these features with any of the other mechanisms that I outlined briefly earlier. Okay, so now things really seem to be appearing out of order. Anyway, just if you'd excuse me for one moment, I just want to see what happened. Okay, all right. Sorry, I gave a different version of this talk recently, so I'm confusing myself a little bit. Okay, so very good evidence in our experiment that ion migration is going on. But I was trained as a physicist, so I'm kind of never really happy that I've explained anything until I can put my explanation into a model of some kind, into a mathematical model. The problem with making models of these phenomena is that we don't really have access to all of the information we'd need. So in particular, we'd like to know, well, what are the lateral potentials that are driving ion migration? There's just no technique that can really easily answer that question, unfortunately. So the best we can do is to make some simplifying assumptions and try to guess what's going on. So I've made little cartoons here to kind of illustrate a process for estimating the lateral potentials in a device. So you can basically draw these little band diagrams, pen and paper. There's nothing particularly quantitative about this. It's just to get an idea of what's going on. And so here I'm illustrating the process of estimating lateral potentials for a device that's held at short circuit. And so the process is for each region in your device. So here we've got our two dead space regions, which are missing one or other of the electrodes, so silver and ITO. basically you draw these little simplified band diagrams in which you place the two electrode potentials at wherever they need to be. So here I'm doing a short-circuited device, so I put them basically aligned with one another. And then you pick the position of the perovskite bands accordingly. So we know that we can get a reasonably good contact with silver, so that implies that the position of the perovskite bands is somewhere down here in this region of dead space, and we get a reasonably good contact with ITO, which means the bands are positioned somewhere over here in the other region of dead space. And then within the active area, we have this kind of familiar PIN type band structure. So that already allows you to guess the direction of ion migration. So you can see here, so it's a high potential for electrons, meaning that negative charges will tend to move in this direction from right to left, whereas conversely, positive charges will be moving from left to right. So that gives you already a kind of qualitative idea about which way ions should migrate across your different boundaries. It's not very precise, but it's at least a starting point. And so that's kind of the one-dimensional picture. If we extend that to 2 dimensions, then this is a kind of a rough sketch of the potentials that we expect across our devices. So on the left-hand side, I've done this for 0 volts, and then at another kind of arbitrary forward bias above the built-in voltage on the right-hand side. So you can see that as you apply forward bias, this kind of orientation of the lateral fields reverses. So initially, as you apply forward bias, you're working against the built-in field, and then eventually these potentials reverse in sign. So that's what I'm depicting on the right-hand side, and I'll return to that fact in a little bit when I come to the next series of experiments. So just to take this modeling a little bit further, and this is all right for a sort of back-of-the-envelope estimate, I wanted to do a little bit better to predict the patterns of ion migration. And so essentially, I developed a class of diode models. They're basically just diode models, which are kind of using flat band type assumptions. So I just assume that my device is characterized by these 2 potentials at the top and the bottom of the device, which just gives me 2 kind of variables to solve for. And then I use a diode model to close the system and actually get a result. So all the details of that are described in my paper. And I'm happy to answer any questions, but basically that's the gist of it. And it allows you to compute these 2-dimensional maps of what the internal potential should look like in your device. Okay, so showing on the right-hand side, the predicted potential for a device that's held at -2 volts. Okay, and then you can go one step further and use that computed potential to drive a drift diffusing ion simulation. So that's now what I've done on the right-hand side. Basically, I've taken that potential, I've driven an ion for a certain amount of time, and I'm showing you the comparison between the experimental PL images and the distribution of ions on the right-hand side. So you can see that it's not an exact match, but there is some confirmation here, at least, that all the features we see in this experiment could be explained quite plausibly by laterally diffusing ions. And you can also use this data to get a bit of quantitative information, in particular by matching to longer-term tests, not the ones that I'm showing here. You can get estimates of the diffusion constant of our species. And in this particular test, I get numbers of about 10 to the -9 centimeters squared per second. Okay, so much for the verification. What are the consequences? Oh, pardon me. So often when we reverse bias our devices, we see pictures like the following. So now I'm showing you the full device rather than just a zoom. So we have activity at most of the boundaries. You can see, so this device before and after reverse bias, we've got darkening at the ITO boundary. We've got something happening at the silver boundary, although it's not as noticeable. And that's in PL. And when we look then at current flow, on the right-hand side, I'm showing the same type of device after reverse bias, and then a little while afterwards, after it's rested. We see this enhancement of forward current passing in the region where there are these patterns of ion migration. So it seems pretty clear that the laterally migrating ions are affecting the current voltage properties of your device. And we know for a good solar cell, we don't want a lot of current passing in forward bias. We'd like the forward current to be as small as possible. So this enhanced current injection in forward bias is not a good thing to see. And this might be responsible for the fact that often when we reverse bias our devices, we see that their performance drops. But if we leave them to rest for long enough, in particular, for our devices, it's often kind of overnight periods of 24 hours or more, they typically recover their performance. So that could be associated with this kind of intense migration happening at the boundaries, which is affecting a current injection, and then that process kind of relaxing over time as you allow the device to rest. Okay, so it's not without its consequences. And in terms of other predictions of this hypothesis, I mentioned a few slides ago that just the built-in field is enough to already drive migration. So question is whether we actually see things happening in the absence of applying any bias. And the answer seems to be yes. So you have to look a little bit closely. The images that I'm showing in these figures are contrast adjusted. But very typically, I see when I look at devices that have been in storage, so before I've even done anything to them, before I've so much as measured them in our solar simulator, I start to see the development of these patterns. And it starts occurring as soon as I evaporate the top electrode. So that's kind of when the clock starts. And then you see these patterns of migration happening progressively over time, even when they're just kept in darkness inside the glove box, so in gas storage. So indeed, it seems like the built-in field is enough. Okay, and then, so what is the relevance to other aspects of stability? Of course, the main stability problem is operational stability, or MPP stability, the reverse bias being a bit of a niche issue. So one of the first things that I wanted to test as soon as I started seeing these patterns is, do we see them in MPP tracking? And the answer is yes. So here I'm showing a cell before and after it was MPP tracked for 100 hours under one sun illumination, and you can clearly see this pattern of modulated PL intensity around the cell boundary. So here around the silver boundary, with this curious little front occurring around the corner. Okay, so again, being careful, we need to ask, is this really lateral migration, or is there something else going on? I mean, I'm sure the perovskite people in the audience will be familiar with papers suggesting that we can have, for example, interactions with the atmosphere. So I've mentioned these loss of encapsulation effects. We can have things coming onto the top of the electrode and migrating around. So it's of interest to really test this very rigorously. And the hypothesis of lateral ion migration actually makes some very specific predictions that we can test. And in particular is the voltage dependence. Okay, I'm seeing there's okay, sorry, distracted by the question there. I'll come to that later. Okay, so yeah, very specific prediction of this lateral migration hypothesis is the voltage dependence, because we see that as we apply forward bias, we start to nullify these lateral potential differences. And eventually, once we cross the threshold of the built-in voltage, the potential differences actually reverse in direction. So we do expect, on the basis of this hypothesis, at least for the particular device architecture that we're working with, we should see a diminishing of effects with forward bias up to the built-in voltage, and then maybe a reversal afterwards. So I wanted to test that prediction. And I did so in a series of experiments where I put cells in our stability tester, and I held them at fixed voltage. So rather than doing MPP, holding cells at fixed voltage, and I picked three voltages, 0, 0.9, and 1.2. So we've got a short circuit condition, kind of moderate forward bias at 0.9, and then a forward bias condition where we expect to be very close or perhaps above the built-in voltage at 1.2. And indeed, we see exactly that it's the short circuited cell that has the most severe effects happening around its edges. So that seems to be fairly good evidence in favor of this ionic hypothesis. Looking at that in a little bit more detail, so I'm showing here images of diffuse reflection. So previous images in black and white have all been photoluminescence, but diffuse reflection is actually quite a useful technique for looking at distributions of degradation, because wherever you have roughening, and degradation is often accompanied by roughening, you have this increase in diffuse reflection. So I'm looking at this little highlighted corner of the device here, where we have four different regions, let's say, of the device meeting in one space. And you can see quite clearly that it's the region of dead space over the ITO boundary that's degrading the most. So that's where we have the brightest region of diffuse reflection, meaning that we have strong roughening in that area. And this degradation is indeed decreasing with applied voltage. So as we go to 0.9, you can see that there's a small little spot of damage happening at that corner, and at 1.2, it disappears. So it looks as if nothing much is happening there. And when we look at our models, it's this region where the ITO boundary finishes that's actually at the highest internal potential, so at the most positive internal potential at 0 volts, which means that the degradation is occurring preferentially in regions at positive relative potential, okay, and diminishing with applied voltage. And this is quite interesting because there have been a number of studies on lateral devices, so not solar cells, but these sort of interdigitated contact devices where you typically apply kind of a large bias voltage between fingers on top of your perovskite or buried beneath it. And usually whenever the degradation is seen there, it's happening at the anode, so at the region at positive potential. So it seems to be consistent with that finding. Okay. So again, I can apply my models to see whether the patterns of degradation here match with what we expect based on lateral ion migration, and the models do quite well. So here I'm showing two different devices on the left-hand side, again, photoluminescence images. They've undergone different periods of degradation, both at short circuit. And you can see the patterns on the right-hand side predicted by the models. So we don't a priori know much about the ion that's migrating here. I mean, a good guess is maybe that it's related to halide defects, in which case you'd expect that it's an anion, perhaps. So halide defects usually, you know, we might think of vacancies or interstitial. So, okay, I mean, it could go either way. So I simulated both cases of having mobile anions and mobile cations. And it seems like the best match to the pattern is the one with mobile cations. So I showed this as sort of my table of contents figure. On the left, a little zoom of this corner region where you have these very intriguing patterns of degradation, including these sort of fronts that are coming off at an angle around the ITO boundary. And the models with mobile cations do a reasonably good job of reproducing this. Some of these features are absent in the models with mobile anions. So I'm tempted to think that it's a mobile cation that's responsible for this damage, but the evidence is kind of not completely in on that. It's a sort of a tentative indication. Right. So going back to the sort of philosophical introduction that I started with, it would be nice to kind of put a box around these phenomena and give a name to this mode of degradation. So I'm tentatively proposing anodic mode as a possible name for these phenomena, because in our devices this seems to be happening preferentially in regions at positive potential. So perhaps as this degradation mode is elaborated, we'll think of a different and better name, but that's what I'm referring to it as for now. So it has a number of unique characteristics. As I said, defining characteristic is kind of that it occurs preferentially in regions at positive potential. As far as I can tell, it only occurs under illumination. So when I've tested devices just at sort of elevated temperature in the glove box with no light, I don't see any of these phenomena occurring. And microscopically, I mean, we did a bit to characterize this degradation mode, looking at devices in PL and in SEM. I'm not going to go too much into detail now, but I'm happy to answer questions. The mode seems to be accompanied mainly by band gap shifts in our mixed halide perovskites and the formation of these voids. So the void formation is kind of what you're seeing in these diffuse reflection images that I showed on the right. It seems to be reported by more and more people now, and so it might be quite a universal feature of perovskite degradation that you have these voids. But the distribution of these voids and their variation with applied voltage is very interesting if you look at the different device regions. So I don't think I'll go into all the details of that now, but it's all elaborated in the paper. So I wanted to spare just a little bit of time to discuss some connections of this degradation mode. So I can see I'm already taking a few more minutes than I intended to. So I'll move on quickly
It's
to
okay. Take your time.
Okay, we're getting there. I mean, I think it's quite interesting to see that this mode of ion-induced degradation is apparently connected to other forms of degradation that we're perhaps more familiar with. So it's been described a few times now in the literature that perovskite devices have this tendency to degrade around points and in a propagating fashion, which is quite bad news. So if you have kind of one bad spot on your device, then very often it'll be a source of degradation that affects the surrounding areas, and you have this propagating front of bad stuff happening to your device. So this was a solar cell device in which I stressed the guy at forward bias. So it's kind of an LED type test where I was applying forward voltage and just looking at the electroluminescence. The schematic on the right shows the region that I'm focusing on here. And the surprising observation was, I mean, I was expecting in this test to perhaps see something happening around the boundaries, so the one-dimensional electrode edges of the device. Instead, I saw this degradation happening at the corners. So you can see that the two corners that I've pointed out with the arrows here are the source of a propagating front of degradation, as well as this little spot, probably a contaminant particle or something that got into my cell, and which is already there in the T equals 0 photoluminescence image. So this has been sped up quite considerably. It was a test that went over about 50 hours. But very interesting to see that this degradation at the corners strongly resembles what's happening at the point of contamination. So what's going on with the corners? It's very hard to understand that as being a point of vulnerability, except if we're thinking about lateral ion migration. So as you can see on the figure on the right, these corners are regions where we have quite strong lateral electric fields, which means that we can expect fairly strong fluxes of ions around these corners. And so I think that's the only kind of really plausible way of explaining why they would be kind of weakest links in the degradation that we see here. But then it's very interesting that it resembles the point degradation. So I think you can understand that. If the contaminant particle here is either obstructing the top or the bottom electrode, because in that case, you would expect the formation of these lateral electric fields, and you might then see precisely the same form of ion-induced degradation that we see at electrode boundaries happening around these contaminant particles. So you can potentially understand this theoretically, that's perhaps what's going on. Okay, so to summarize, and this is really just kind of the beginning of elaborating these effects, but we can see that clearly ions are moving laterally in our lab scale devices, and that there's really no such thing as inactive area when we're thinking of these ions moving around. So it's a bit of an inconvenience, but that seems to be the case. There are impacts on cell performance and stability, so this matters. I've showed you that it matters in reverse bias, and it clearly also matters for MPP tracking and looking at the operational stability of our cells. Unfortunately, all the impacts of this are going to depend on the dimensions of your device. So a lot of these devices that I've been showing you are extremely small. So I make small devices to help, well, it makes it easier to characterize exactly what's going on, and I can avoid as much contamination as possible. So the results that you get are going to depend on the size, so the dimensions of your active area, which unfortunately introduces this problem of comparing results between different labs potentially that are working with different device areas. And finally, yeah, it seems as if these ion-mediated edge effects are not kind of an isolated phenomena necessarily, but perhaps connected to other more familiar modes of degradation that we've seen before, in particular these point and propagating modes. So that's kind of the end of the technical part. I just wanted to finish finally by coming back to the philosophical stuff at the beginning. So what I've described here is one mode of perovskite degradation that I think we ought to be looking out for now when we report stability of devices. So in order to sort of diagnose this type of degradation, it's clear that we need to do more than simply measuring MPP efficiency. Although of course that's the starting point. So I think it would be great if, in addition, as a community, in addition to these MPP measurements, we started providing things like images of our degraded devices. So whether that's an optical image or a PL image, EL, lock-in thermography, of the entire active area so that we can see whether the degradation that's showing in the MPP data actually represents something happening uniformly across the device, or whether it's related to edges or particles or something else. I mean, I think that it would be good if that was kind of part of standard practice in reporting. And I've sort of given a list here in perhaps order of importance. It would also be nice to do sort of post-mortem testing in which we look at the innards of our degraded devices. So looking at, for example, the formation of voids, as I showed very briefly in one of my slides, looking at cross sections, and also doing post-mortem material characterization to see what's happening in the degraded areas. So I think if that were to become more sort of standard practice, it would be really helpful to deepen the understanding of different degradation modes, to see, are we all actually addressing the same sorts of issues? And then we can start to think about strategies for moving forward. So that's that.